I'm Seonyeong from Kyung University, and thank you for the introduction. So in this talk, I'd like to introduce our work on TinySeg model optimizing framework. So tiny machine learning is to enable machine learning models on tiny embedded systems like Arduino Nuclear Vision on this slide. So the size of this device is just 2 centimeters by 2 centimeters long. And these tiny embedded systems often use a low-power microcontroller with a very small size memory. So thanks to the benefits in various aspects, tiny machine learning is getting more attention in both industry and academia. However, in tiny machine learning, small memory size is regarded as the main limiting factor. So while the tiny embedded systems has a memory size of less than 1 megabyte, state-of-the-art machine learning models are much larger in size. So it is very important to optimize the memory usage of machine learning models in tiny machine learning. So our target task is image segmentation, which is to classify each pixel of input image into a certain category. So UNet is one of the most well-known image segmentation networks. So this network has this hourglass-like structure with these long skip connections. So along the skip connections, early results are concatenated with the later results. So we analyzed the memory usage of an image segmentation model on top of an existing tiny ML framework. So basically, to execute a model on the target system, 2 types of tensors have to be stored in memory. The first one is parameters, which are the weights of the model. Usually they are fixed after training. And the second one is activations, which are the intermediate results from the input data. So I measured the memory usage of parameters and activations for the segmentation model and a typical classification model. And here we found that even if the segmentation model has less number of parameters, actually it requires much more memory space for its activations. So that is, the segmentation is smaller than the classification model, but requires more memory. So this is why the segmentation model cannot run on the tiny embedded systems. So we investigated why the image segmentation models have such high peak memory usage and found 2 major optimization blockers. And then first one is large long-living tensors. And the second one is large interim tensors, especially used for concatenation. So the first optimization blocker is long-living tensors, which have this long lifetime along the skip connections of the network. So since the memory space cannot be shared when the tensors are alive, so these long-living tensors may contribute to the peak memory usage without being used for a long time. And the second optimization blocker is large interim tensor for concatenation at the end of these skip connections. So they usually need large memory space to concatenate 2 tensors into 1 tensor. So they may also increase the peak memory usage of the model, even though they are used only for a short time. So our main idea for overcoming the optimization blockers is dynamic tensor spilling. So in dynamic tensor spilling, long-living tensors are spilled into the local or remote storage before they become idle. And then they are fetched again from the local or remote storage before they are used again. So it can reduce the lifetime of the long-living tensors by spilling the tensor into the storage, and then also it can remove the large interim tensor by integrating the fetching process with the following operation. So to support the dynamic tensor spilling, we propose a new model optimizing framework called TinySeg. So this framework consists of TinySeg model optimizer and TinySeg runtime. So this model optimizer takes a TensorFlow-like model as an input and interprets the model as a graph, and then it generates a memory plan for checking the peak memory usage, and then it analyzes the code range of the tensors, and then transform the graph based on the code range analysis results. And then it outputs the optimized TensorFlow-like model. And then the TinySeg runtime takes the optimized model and provides some custom operators and tensor transfer module that will implement the tensor spilling. So the code range analyzer analyzes the code range of each tensor, where the tensor is just stored in memory without being accessed. So it tracks the longest distance between def and use, or use and use from the root of the graph. So based on this analysis result, the graph transformer selects the victim tensor to be spilled and transform the graph to insert corresponding operators. So the graph transformer first insert this spill operator to spill the tensors into the storage. And then it inserts the fetching operator to fetch the tensor from the storage at the end of the code range. So after the transformation, the lifetime of the victim tensor will shorten so that the memory space can be shared with other tensors. And after that, the graph transformer tries to fuse the fetching operator with the following operator, because if the fetching operator outputs the large interim tensor, then it tries to fuse the fetching operator to remove that large interim tensor. So the TinySeg runtime provides various optimizations to reduce the tensor spilling overhead and further optimize the memory usage. So the first optimization is bitmap-based tensor compression. So it is very simple compression scheme, which identifies the most frequent value in a tensor. In this example, it is -9, and then uses a bitmap to indicate the locations of the same value, so that it can avoid storing the same value multiple times. So it can reduce the size of the tensors to be spilled. And the second optimization is asynchronous block operation. So when the tensors are spilled into the local flash memory, the flash blocks have to be erased first to be written. So here, block erase takes much longer time than the read or write. So we propose to use another process core to hide the block erase latency via remote procedure call. So it can reduce the spilling overhead. And the third optimization is temporary tensor quantization, which is to quantize the temporary tensor used in the operators to reduce the peak memory usage. So for evaluation, we implemented our prototype framework on top of TensorFlow Lite for microcontrollers, and our implementation is available at our GitHub repository. And to test the image segmentation on top of tiny embedded systems, we created a tiny unit model which has 100,000 number of parameters. And then to measure the latency of the model, we used Arduino Nicla Vision, which has dual ARM core, M7 and M4 cores, and with memory, 1 megabyte memory and internal and external flash memories. So we examined how the peak memory usage changed when we apply the proposed method step by step. And then after we apply the temporary tensor quantization, we could obtain 22% of memory size reduction. And then when we apply tensor spilling and fused fetching together, we could obtain the final memory reduction of 39%. So we also measured the end-to-end network latency with different spilling targets on Arduino NickleVision. So the first option is to spill the tensors into the internal flash memory inside the microcontroller. And the second option is to spill the tensors into the external flash memory outside the microcontroller. And the third option is to send the tensor data to the remote host via serial communication. So even though the tensor spilling results in doubling the latency of the model, we successfully reduced the overhead of tensor spilling by tensor compression and asynchronous block erase. So at the end, we only got 6% of overhead to obtain the 40% of memory reduction. So let me conclude my talk. So Tiny Machine Learning aims to enable intelligent services with machine learning algorithms on tiny embedded systems with small size memory. So this work introduces a new model optimizing framework, which reduces the peak memory usage of a model with tensor spilling and fuse fetching. So with the evaluation results, we could show that the proposed framework can help deploy more intelligent models on tiny embedded systems. So thank you for your attention, and I would be happy to take any questions.
Thank you for intriguing question. I believe that you are explaining about the mechanisms to optimize the TinyML models. And can you explain briefly about the strategy you use? For example, which tensors are going to be spilled as a victim, or other kinds of strategies?
Okay. So to select the victim tensor, we first find the tensors that contribute to the peak memory usage of the model, and then selects the tensor with the longest code range. That means the tensor is stored in the memory for a long time without being accessed. So that would be the victim tensor. So it repeats, trying to spill the tensors until it reaches the target memory usage. Yeah, the details are already in the paper. Yeah, thank you.
Maybe two questions. First, so when you spill the tensor to the flash memories, did you consider the lifetime of the device? Because I think the flash memories of this controller has a limited lifetime.
Yes, that's a great question. So the number of block erases is limited in flash memory, but at the moment we don't consider the lifetime of flash blocks. So I think ideally we have to distribute the tensor data into different flash blocks, but yeah, at the moment, it is not implemented.
And other questions are related to this slide. I'm a bit confused. So you say latency for remote case is a lot faster than using internal flash and external flash memories.
Yeah, actually, it was interesting to see how remote spilling is faster than the internal spilling.
Because the remote is using the serial communication.
Yeah.
Right?
We used the USB connection to transfer the tensor data to the host. So the USB connection was quite fast. And this for internal spilling, we have to endure the block erase latency. So if we hide the block erase overhead, then we could obtain much better results than remote spilling. But with the block erase overhead, the local and external spilling works.
Thank you so much.
Yeah, thank you.
Hello.